Gamma rays are one of the most energetic forms of light in the universe, but they do not look like light to us. You cannot see them, feel them safely, or block them with ordinary clothing or a thin wall. They are electromagnetic radiation, like radio waves, microwaves, visible light, ultraviolet, and X-rays, but they sit at the extreme high-energy end of that family. A gamma-ray photon can carry enough energy to disturb atoms, strip away electrons, and damage the molecules that living cells depend on. That is why gamma rays are called ionizing radiation. They are not mysterious magic beams, they are packets of energy moving at the speed of light. What makes them so important is the combination of invisibility, extreme energy, and deep penetration through matter. To understand gamma rays, imagine the electromagnetic spectrum as a scale of energy. Radio waves have long wavelengths and low photon energy. Visible light occupies a tiny middle region that human eyes can detect. Ultraviolet light is more energetic and can already damage skin. X-rays go further, passing through soft tissue and revealing bones. Gamma rays go beyond that. Their wavelengths are extremely short, and their photon energies can reach levels associated with nuclear reactions and violent cosmic events. At the lower end, gamma rays overlap with high-energy X-rays, so the boundary is not always simple. In many fields, the name depends less on energy and more on origin. If the radiation comes from the atomic nucleus, it is often called gamma radiation. That origin-based distinction matters because X-rays and gamma rays can look similar once they are traveling through space. Both are electromagnetic waves. Both can ionize atoms. Both can penetrate matter. The difference is often the process that produced them. X-rays usually come from energetic electrons outside the nucleus, such as electrons slowing down rapidly or jumping between inner atomic energy levels. Gamma rays are commonly produced when an unstable atomic nucleus releases excess energy. Astrophysics sometimes uses a more practical definition: radiation above a certain photon energy, often around 100 kiloelectronvolts, is treated as gamma radiation. So the word gamma ray is partly a label of energy, partly a label of origin, and partly a convention used by different scientific communities. The discovery of gamma rays came from early radioactivity research. In 1900, French chemist and physicist Paul Villard was studying radiation emitted by radium when he found something unusually penetrating. Scientists already knew about alpha and beta radiation, but this new emission traveled through materials more effectively than either of them. Ernest Rutherford later named it gamma radiation, continuing the Greek letter sequence he had used for alpha and beta rays. At first, the names simply ranked how easily each kind of radiation passed through matter. Alpha rays were stopped easily, beta rays went farther, and gamma rays penetrated the most. That simple observation opened the door to a deeper understanding. Radioactive atoms were not just emitting particles, they could also release extremely energetic electromagnetic radiation. A major source of gamma rays is radioactive decay. Inside an unstable atomic nucleus, protons and neutrons may be arranged in an excited state, meaning the nucleus contains extra energy. When it settles into a lower energy arrangement, that excess energy can leave as a gamma ray photon. These gamma rays often have energies from tens of kiloelectronvolts to several megaelectronvolts, which reflects the energy gaps inside atomic nuclei. This is very different from visible light, which comes from much smaller energy changes in electrons. Nuclear energy levels are larger, so the emitted photons are much more powerful. In this sense, gamma radiation is like a signal from the nucleus itself, carrying away energy as the atom becomes more stable. Because gamma rays from radioactive decay have specific energies, they can be used as fingerprints. Different radionuclides emit gamma photons at characteristic energy levels. By measuring those energies, scientists can identify which radioactive materials are present, even if the sample is hidden, mixed, or too dangerous to handle directly. This technique is called gamma spectroscopy. It is used in nuclear power, environmental monitoring, border security, medicine, archaeology, and laboratory research. The detector does not simply say that radiation exists, it measures the energy pattern and compares it with known nuclear signatures. That turns gamma rays from a hazard into information. The same radiation that requires shielding can also reveal the identity of invisible radioactive substances. Gamma rays also come from beyond Earth. The universe produces them in extreme environments where particles are accelerated to enormous energies. Solar flares can release gamma radiation during violent magnetic eruptions on the Sun. Compact objects such as neutron stars, black holes, and microquasars can create gamma rays when matter is heated, crushed, accelerated, or forced into powerful jets. Very high-energy gamma rays have been observed from astronomical sources, reaching energies far above ordinary nuclear decay. For astronomers, gamma rays are messages from the most energetic processes in space. They reveal events that ordinary visible telescopes may miss completely. Studying them helps scientists trace cosmic particle acceleration, explosive stellar behavior, and the physics of matter under extreme conditions. Earth has natural gamma-ray sources too. Some come from radioactive elements in rocks, soil, and building materials. These materials are part of normal background radiation. Other gamma rays are created when cosmic rays from space collide with particles in the atmosphere, producing cascades of secondary radiation. There are also rare terrestrial gamma-ray flashes associated with thunderstorms, where intense electric fields accelerate electrons and trigger bursts of high-energy radiation. These events show that gamma rays are not only produced in reactors or distant galaxies. They are part of the planet's natural radiation environment. Usually, the levels around us are low, but the sources are diverse: underground minerals, atmospheric collisions, lightning storms, and the constant arrival of energetic particles from space. Humans can produce gamma rays artificially through nuclear and high-energy processes. Nuclear reactors generate gamma radiation from fission and from the decay of radioactive fission products. High-energy physics experiments can produce gamma rays when particles collide or when unstable particles decay, such as neutral pion decay. Fusion research can also involve gamma-producing reactions. These artificial sources are valuable but carefully controlled, because gamma rays travel far and penetrate deeply. In nuclear facilities, gamma radiation is monitored constantly with detectors and dosimeters. Workers reduce exposure by limiting time near sources, increasing distance, and placing dense shielding between people and the radiation. Gamma-ray safety is not based on fear, it is based on measurement, planning, and strict control of dose. The biological danger of gamma rays comes from ionization. When a gamma photon enters living tissue, it may pass through without interacting, or it may transfer energy to an electron. That interaction can break molecular bonds, create reactive chemicals, and damage DNA. If a cell repairs the damage correctly, it may survive normally. If the repair fails or introduces errors, mutations can result. Over time, those mutations can increase the risk of cancer. At high doses, the damage is immediate and severe, causing burns, radiation sickness, bone marrow injury, and harm to internal organs. Gamma rays are especially concerning because they can reach deep tissues, unlike alpha radiation, which is stopped by skin, or many beta particles, which are easier to shield. Shielding gamma rays is difficult because they are so penetrating. A thin sheet of paper stops alpha particles, and a modest layer of material can reduce many beta particles, but gamma photons require dense or thick barriers. Lead is commonly used because its high density gives gamma photons many chances to interact and lose energy. Concrete is also widely used, especially around reactors, accelerators, and radiation storage areas, because large thick barriers are practical and affordable. Shielding does not always eliminate every photon, instead, it reduces intensity to acceptable levels. Designers calculate how much material is needed based on photon energy, source strength, distance, and allowed exposure. Gamma protection is therefore a combination of physics, engineering, and disciplined procedure. Detecting gamma rays takes special instruments, because our senses give no safe warning. Scintillation detectors use materials that emit tiny flashes of light when struck by gamma radiation. Semiconductor detectors can measure photon energies with high precision, making them useful for identifying radionuclides. In astronomy, detection is harder because Earth's atmosphere blocks many gamma rays before they reach the surface. That protection is essential for life, but it forces scientists to use satellites, space observatories, or indirect ground-based methods that look for particle showers created when very energetic gamma rays hit the atmosphere. In every case, gamma rays become knowable only through their interactions with matter. We do not see them directly, we reconstruct their presence from the traces they leave behind. Gamma rays are dangerous, but they are also useful when controlled. In medicine, carefully directed gamma radiation can help destroy cancer cells. In industry, gamma rays can inspect welds, pipes, and dense structures without cutting them open. In sterilization, they can kill microorganisms on medical equipment and certain materials. In science, they help identify radioactive isotopes and reveal nuclear processes. The lesson is not that gamma rays are simply good or bad. They are powerful. Uncontrolled exposure can harm life, but controlled use can diagnose, treat, inspect, and discover. Gamma rays connect the atomic nucleus to the largest cosmic explosions, and they remind us that some of the most important forces in nature are completely invisible until we learn how to measure them. If you found this helpful, please like this video and subscribe for more explainers.